Alright guys, welcome. In this live, we will discuss about GNNs, okay? GNNs, graph neural networks, okay? Like what is graph, right? It's like some friends group, like A is friends with B is friends with C, and C is friends with D, right? And B is friends with D also, like this. This is graph, right? Or we can say subway map, like this point is connected with this point, and this point, like this, right? This is how maps looks like, right, on subway. So these are graphs. They have some nodes and they have some edges which connects those nodes, right? You already know, because if you are understanding what is GNN, so you already know. If you are try to understand neural networks, you should already know what is graph, right? So I am assuming like you know basics of like this. So here is a question that sounds simple, but it will break most of machine learning models, okay? So look at these four things, like a group of friends, or a molecule, a subway system like this map, and the pages of Wikipedia, they are also connected like a graph, right? What do they have in common? What do they have in common, right? All of them. So common thing in this friends group, let's take only these two examples and there's a subway map, right? These are two maps. What is common between these two? Don't stress your mind. I am telling you. The common thing in both of these is none of them, right, fit in a spreadsheet. But every model you have probably trained till now, okay? Every image classifier, like every spam filter, anything, any model till now, right? They will expect a clean table, right? The data, they expect you in a clean table. The model expect you a clean spreadsheet of data from you, right? Like one row per example, well, one column per feature, like that, right? But the world isn't row or columns, right, guys? The world is connections. Who knows whom, who wants to vote, like this, right? What links to where. The world is connected like a graph. This is not a spreadsheet, right? So what is valuable, right? In this case, what is valuable? Is it the node, right? Or is it the edge? What is valuable in this graph? So answer for this, guys, is the value is int in the node, okay? It's in the edge. So to understand this, what I mean by this, we have to watch this live entirely, right? By the end of this video, you will not just understand graph neural networks like, oh, these, okay, by theory, right? By as a concept, oh, this is a graph neural network. What is, you just omit your definition. It's not like that. You will build one from scratch and plan NumPy here, okay? Watch it, learn, and then rebuild it with the same tools professional researchers use, okay? All in this video, whatever tool we use will entirely free, okay? And we are going from what even a graph to a graph transformer, okay? In this video, what we will go from a graph to a graph transformer. Alright, it's very interesting. Like from zero to expert in GNN, okay? So let me change the title of the video also for you. What is the title? Right now title is GNN code with the like GNN 0 to expert, like this, okay? Then let's start. What are the prerequisites for this video? Like let me be honest with you about what you need walking in the video, okay? So nobody will feel lost and nobody feels bored in this video, right? Everyone understand what is going on. Like prerequisites are like this, not much but just basics, okay? First, I should be comfortable, like I am assuming you should be comfortable with Python basics, okay? Like what is a loop, what is a function, right? And list, what is list in Python, like this. And you should have seen a neural network before. What a neural network, like how they learn, right? Like dimensions, right? Output, input, right? Like what are the functions they use, activation functions, like that. You should have seen them, because that's why you are on GNN, right? You must have like seen at least once and build something little bit. But don't worry, we will build things here also, and at least enough to know that training means adjusting weights to reduce error, right? How to train in GNN, neural network, what that training means, right? So it means like adjusting weights to reduce errors, and you should know like what is the weight and we are using them, right? If those words are fuzzy to you, so you should watch a 5-minute, 10-minute neural network basics premiere. Like if you don't know like how they train and learn, then you can come back, right, and watch this video. So you don't need to know graph theory entirely. You do not need to heavy linear algebra here, right? When we hit matrices, I'll walk every single number by hand for you. That's a promise. So that's not like, okay, you need to be expert at everything. Just Python basics, and you know like what training means in neural networks. That's only prerequisite for you in this video, right? And I hope like in this AI world, you must have watched this 5-minute, 10 minutes neural network videos if you are an engineering student, and so that's expected from you. If not, then what to do we do, okay? So we set up environment right now first. Okay, so there is two paths for you. Okay, everything today is free, no tools we pay for. Okay, so path A is for environment is like we do not install any GNN install, right? Like we can use Google Colab for that, right? So Google Colab, if you don't know, you can go to like colab.research.google.com, and there you find click on new notebook and you are free, right? So there you will get a free Python, free GPUs, nothing on your machine, right? On screen browser at colab.research.com and click on new notebook, you will get everything there. So you don't need to install Python, you don't need to run your code in your machine. Your code will run on cloud on Google's GPUs. Okay. Path B is path B is local. If you rather run it on your own machine, here is the exact setup. Like you install your Python, okay, and create a virtual environment for your isolate project like this. Let me tell you how we are going to do this. Let me for new window. Okay, can I see this? No. Alright, so new window is not there. I have to file open folder, right? I have to open some folder, and daily is good, right? Yeah. Open this. Okay. Yeah, I trust that this author, and there are some files. I will delete this also. Right? To set up environment locally, what you need to do, open your terminal in your folder, okay, and check is there any Python installed already in your system or not, right? So there is no Python for me here. Okay, so I need to install that. And if you can install like so let me tell you why I am not doing this here. Okay, let me do it for you guys, right? No, okay, so if you are not finding any Python, don't worry. What you need to do, guys, is you need to create a isolated Python environment here, virtual environment, to run your Python. That Python environment is not anything, just there is that it will tell your system like where to find your Python, right? So we are installing separate Python for this folder, right? So let's go Python mvenv, right, virtual environment, and we are going with both GNN environment. Okay, command Python not found. Okay, so okay, pip install Python, I think. No, okay, so sudo install Python. No, okay, let's go for this like Python 3. Okay, M V E N V GNN ENV. So sometimes what happens, I am on Ubuntu Linux, right? So the problem is, guys, that Python is not like direct command entry, right? In Linux Ubuntu I am using Python 3, and like sometimes Python works, sometimes Python 3 works, right? Like this, there is no much difference, not one single difference. Okay, so here what happens, it's create a virtual environment, and you can see here. So there, this is my Python 3.12, right? Now what happened here is like they create a virtual environment. Now anything whenever I run Python, this will point to this Python. Okay, not like anywhere else I have installed Python, so it will not like install like point there. It will learn from this Python. Okay, just that's it. Now I will point this to this directory also, like how we do source. For Windows, if you are using Windows, you have to just like do is GNN ENV / scripts. Okay, not like this slash. Okay, scripts / activate. But for Linux and Mac OS, guys, this is your command. So GNN ENV. Okay, bin and activate. We have to activate this script, guys. Okay, this script here, right? Now you can see like GNN ENV is like, now this root is pointing to, this path is pointing to this folder, right? That's what I'm saying. Now we will install some when you do this, when you have this environment, then what you can do is you install some libraries. Okay, all of them are free, just install them. pip install okay, all of these you get free for on Google Colab, so you don't need to install them, any of them, right? Just install here numpy. Okay, pip install numpy and matplotlib. Then we have to show network kx. Okay, network x. These are all libraries we have to work with, and after this we have to torch, and other is torch geometric. Okay, so install all of these, and after this and like I have just remind you, like sometimes on local installs, like this torch geometric, right? This library sometimes wants a matching PyTorch build for you, right? This torch matching PyTorch. Okay, so if pip install torch geometric throws some wheel error for you, right? So the fix is to just use Colab, right? You can move Colab, it is all free and everything is compatible there. Second, if Python runs Python 2 on your system, so what you have to do is use Python 3 everywhere instead. That's what I'm using, right? Now setup is done, so I think it's downloading torch. Okay, all right. Write code by okay. Till then it's installing. We start from some theoretical concepts first, right? So what a graph really is. Okay, So let me introduce the example we will carry through this entire video. Okay, we will like theory, then we will understand the math of it, then we code it. Okay, all use this same title. Okay, so let's say you have these 5 nodes. One node, okay, 0 is, this is node is n. Okay, then there is a node ben 1, then there is a node kara, okay, 2. All right, like this. These are nodes, these are some all friends. Okay, this is Dev and this is Ellie. Let's say these are 5 friends are there. Okay, Anna, Ben, Kara, Devon, Ellie, and we these are all like circles. Okay, all right, these are pupils. Now we call every person a node, right, or a vertex in graph, right? Now we connect one who study together with a line. Okay, and we call them as edges. So what happens is Anna studies with Ben. Okay, and Anna studies with Kara, and Ben studies with Ellie. Oh no, because they study with together, so Ben study with Kara, this, and Kara studies with Dev. Okay, in some other class, maybe, I don't know, we don't know, right? And Dev studies with Ellie, like this. Now that's it, that's a graph for you, right? Like a graph is just things there and the connections between them. Things are like these and connection are these. Okay, so here is a crucial part for you. The whole region we need new models. So in a normal table, Anna's row knows nothing about Ben row. Okay, we are like running with low disk space, guys. I don't know where I lost my all of my so that's what I am saying, guys. I am not trying to, you can do these things. Okay, I am stopping this, and I am also deleting this because I need free space. I will use Google Colab. Okay, I will not use here anything. I am deleting this and everything because I don't have space. Okay, now I will go online and search. Okay, search.google.colab. Okay, you can search like this. If you can see me, all right. Oh, you can't see me. All right. So okay, now you can see it, right? I am going here and a new notebook I am giving. Okay, give me new notebook and it's loading. All right, yeah, this is environment for you. You don't need to start anything here, right? I need a code cell, so it's a code cell. Okay, So uh, okay, so we come back, we will start coding when we are here, right, okay. So like in a normal table, right, we have ANA, right, in a normal table data, okay. Like this is table, this is for ANA record, this is for ban record, this is for what is LE, right. These record like, okay, ANA studies 8 hours, math 6 hour, like this, height of ANA is this, goes to this school like this, okay, and this on everything. They don't know anything about them, right. This is the normal table we have in a normal data table, right. They are all independent in this case, but in real world NI is influenced by who she study with also, right. The connection carries the information. So a graph keeps both the features of each thing, right. So how many hours in a course versus games each week, okay, and the structure that connects them. Tables throw the structure away, graphs keeps it, okay. So let's give each one if a feature vector, okay. Like how many hours, this is a feature vector, like code, how many hours they code, and how many hours they game, okay. So let's say Anna codes 1 hour and 0 hours game, okay. For ban it's like let's say 0 1, okay. For Kara it is 1 1, let's say, and for Dave it could be 1 0, right, and Ellie 0 1, like this. Carry code. So coding hours and gaming hours per week, okay. So this is like simple for clean structure and calculations, right? Because we are doing everything in hand, we don't want like complicated computations, right, by hand. So that's why I put, you can put any hours here, like 1 5, like this, okay. That's not a problem. So our goal will be to predict a label for each person, like say on a CS track or not. Like one person is on a CS track or not. Like if Anna is giving 1 hour per week on coding and 0 hours to game, so she is like on CS track, right? But Ben is not doing any coding, so he is not on a CS track anymore, right? And the bet of a graph neural network is that who you study with help. So if Anna and Ben are studying together, right? So Anna is going CS track, okay, CS track, and it's not on CS track. But if Anna is studying with Ben, then Ben could be also on CS track, right? So this will help us to predict like who is on like CS track or not. Like it is not just by Anna's hours or not just by Ben hours, right? Just by, it is by who they study with also. So let's make this more precise, because you will see this exact notation in every paper, okay. So we are going mathematically from now, okay. We write a graph as a pair, Like, you understand this? Everything, right? Now, like, graph is this. So, a graph G is defined as the pair of V and E. V is what? Vertices, or we can say nodes, and E is edges. Okay? Or like, this is a set of edges, okay? Set of edges and set of vertices. Okay. So that's whole set will give us the okay. Don't worry, we will manage it. All right. So a graph G is defined as the pair. All right, we have done this. Okay. So for us, what our graph is, what our V is. V is like we have zero node of Anna. So we are not taking names, because in mathematics you can't like compute names, right? So we compute with numbers. Okay, one node, second node, third and fourth. Five nodes are there, and how many edges for you? Edges is equal to this. 0 is connected with 1, right? 0 is connected with 2. 1 is connected to 2, and 2 is connected to 3, and 3 is connected to 4. You can see here. Here, 0 is connected with 1, like this. 1, 2, 2, 3, 3, 4, and 1, 2, and 2, 3. Okay? Like this. These are the edges for us. So this is the exact notation you will find in every paper. And mathematically, we write this graph as pairs of V, set of V and set of E, right? Now, computers don't draw circles and lines, right? They need numbers. So we store the structure in a grid called a adjacency matrix. Okay. So what we can do, because we have to store them, right? So computer don't draw like 0 is connected with them. They don't draw edges, right? So how they store these graphs? So how many nodes we have? 5, right? Let's take a line here. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, like this. All right. 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 1, 2, 3, 4 and 5. Okay. It's little asymmetric, but you don't care, right? 0, 1, 2, 3, 4. 0, 1, 2, 3 and 4. Okay. Now so rule is simple, right? Row of I, this is rows, right? These are rows and these are columns. You know how matrix works, right? Row I and column J gets a 1 if there is an edge from node I to node J. So is there an edge from 0 to 0? No. Is there any edge from 0 to 1? I think yes. 0 to 1. So this entry will be 1. Is there a 0 to? No. Alright. Okay. Now if a 0 is connected with 1, like 0 is studies with 1, so 1 also studies with 0, right? Like this. But there is a self reference also, because 0 is also studies with 1, right? So uh, everything will be 0 else, okay? And 1 is connection, okay, and 2 also connects with 0, like this. Like our friendship is go both ways, like this, okay? Anna studies with Ben, then Ben also studies with Anna, right? So this matrix is symmetric because it's both ways, right? When there is no direction, right? Because bidirectional edges are there, so there is no direction. Like, okay, only Anna study with Ben, 0 study with Ben, but Ben does not study with Anna. It's like this. 1 is connected with 0 and 0 is connected with 1. It's both ways. So this will build a symmetric graph for us, okay? And also we call it a undirected graph because there is no direction in this, right? So how this graph will look like for us? 3 and 4 is there is no connection, like this. Let me fill for you. 0 0 1 1 0, because 2 is connected with 3, like this. 3 0 0 1, no, this is 1, and this is again 0. It's meshed, okay. Alright, this is 1, 3 is not connected with this, and this is 4 1, and 4 is only connected with 3, right? So like this, or everything is 0. So there is subtle and but important idea. Sometimes connections only go one way, okay? Imagine node 0 is a student and node 1 is a teacher, okay? Within edge, meaning like who is a student, like let's say there is a 0 node, this is a 5th node, this is teacher, and the edge defines the relationship between them, okay? The student of, so this will go for 0 is student of 5. This edge will not go like this because 5 is a teacher, this is a student, right? So 5 is not a student of 0, 0 is a student of 5, so it is directed edge, right? And it's a unidirectional relationship, and these type of graphs called the directed graph. We will not go into them right now. Okay. Okay. So, but our friendship is graph is undirected right now. So keep both pictures in your head. Like it can be both, right? Like real data can be both. Like they can have unidirectional relationships and bidirectional relationships also. And one more distinction you will hear constantly, guys, is like our graph has one type of node, like pupil. They are pupil and they are connecting with one type of edges, like studies with, right? 0 studies with one. What is 0 and 1? They are pupil, right? And one type of edges. So these, like one type of nodes and one type of edges, these type of graphs called homogeneous graph, okay? But the moment you mix the types, let's say you have pupil and courses and edges like enrolled in and studies with, so different types of nodes and edges, so those graphs are called heterogeneous graph, okay? Like same core ideas, more bookkeeping to have, okay? And now we come back to GNN little bit because we know the graph. Now we have to move to neural networks also. So what a neural network and GNN do? So one idea behind every GNN is message passing. Okay. So how does a model actually use this structure? So, and every architecture we cover is a variation on it. It's called message passing. Okay. So this message passing is a single most important idea in this entire video for you. And every architecture we cover is a variation of this idea. Okay. But core principle is this. So what is message passing? Let me write it in red. Is it red or what? Okay, whatever it is. So what is message passing? A node. Okay. A node updates itself using its neighbors. Alright. This is called message passing, guys. Like a node does not make a decision alone. It looks at its neighbors and gather information from them and updates its own representation. Then it does it again, and this happens in layers also. So let's watch Anna, then its neighbors, right? So Anna was on node 0, right? Node 0 was Anna. Okay. So in layer 1, we can see what is layering. I said like this happens in layer, right? What is layer? Layer 1, what is layer 1 for Anna? Layer 1 for Anna is her immediate neighbors, right? One is Ben and one is Kara. Okay. Now, in layer 1, Anna will pulls in what they know. Now, Anna's representation is blend of herself plus Ben plus Kara for layer 1. Okay. In layer 2, Anna looks at her neighbors again, but okay, so this is like this, but when this is for layer 1. Okay, this layer 1 happens for everyone, like Anna goes for its neighbors, Ben goes for its neighbors, Kara goes for its neighbors. Layer 1 done for everyone. Okay, when layer 2 happens, right, Anna looks at her neighbors again. Okay, this is level 2. Anna goes for again, right, and again. But what this time happens? This time Ben and Kara already looked at their neighbors. Okay, without ever talking to Dave directly. Okay, so Ben and Kara already talked to their immediate neighbors. Now, when Anna tried to talk with Ben and Kara, they already talked to their neighbors. Okay. So what happens for Anna now? So without ever talking to Dave, like Ben is connected to Dave, right? So without ever directly talking to Dave, information about Dave reaches to Anna in second layer of pulse, right? Okay, like this happens. Kara is connected to Dev, right? So 0, this is 2, right? And Dev is 3. So what is this? 0 goes to 2 and 2 goes to 3, like this hops, right? That's the magic. With each layer, a node sees one hop further into the graph. Okay. Alright. So one layer immediately friends, okay? Two layer means friends of friends. So stack enough and a node feels the shape of the whole network. Like we go layer by layer till one person will fill the whole network. This is how a GNN learns both local patterns and the global structure at once. Okay. Every message passing layer is 3 steps. And I want you to memorize these 3 words. Okay. Because the code later is literally just these 3 functions. Okay. What is what every message passing layer has? These 3 words. Okay. One is message. What is the message? Each neighbor packages of information to send, usually just current feature vector. Okay. Sometimes the weighted by the edge. So we will see like how weighted by the edge means, but we discussed the feature vector, how many hours one studies, right here. So what happens what is the message? Message is just a feature vector of a node, right? So sometimes, okay, so what Anna will get from Ben, she will get this Redmi, this feature vector. Okay, she will get this. Okay, and from her also direct immediate neighbors, her feature vector. All right. Then what is second thing? Let me write everything here. Should I write everything here? Yeah, I think I can. Just erase this. Then we can write things here, right? What is the message? Okay. Message is feature vector of a node, right? Then second thing is aggregate. What is aggregation here? Now Anna will combine all the incoming message into one. How she will combine that? So simplest choice are sum. Like we can sum them all the vectors, we can take the mean of those, or we can take the maximum. Okay. So fancier ones weight some neighbors more than others. Hold that thought, like what we can do, right? How we can aggregate. Anna is what? CS 10, right? This is Anna 10. This is for Anna node, right? We can sum them up all, like 0, 1. Wait. Right? Then we add them 0, 1, like this, and plus this is for Dave, right? No, Ben and Kara. Kara is 1, 1, and this is 1, 1. This is Kara. We can add them. We can take by adding then mean, right? We can take mean also, add mean, and like we can do multiply this, because this is Ben has more influence on Anna, so then multiply by 2 it, like weight. I am giving more weightage to Ben, right? She has, like, Ben has more influence on Anna. Kara has no influence, then 0. We can like multiply by 0 also. there is no influence, so no need to like add her, right? If it has like most influence by Kara, then multiply by 4, like this. We can do this also. So right now, hold this thought in your mind, like weighted and everything. You just know the methods, like aggregation is this, right? It's the whole idea behind the attention, like the weighted and everything. So we will get there also later, right? Now third thing is update. Update, right? What is update here? Anna takes her aggregated neighbors information, mixes it with her own old features, okay, and pushes it through a learnable weight matrix and a non-linearity, and comes her new richer representation. Like what she will do, it's her, there is a message of her, she will get messages, then she will aggregate them, right? After aggregating, she will update. So this loop will repeat across layers, and it's a graph neural network for you. Everything else is GCN, graph sage, GAT, GIN, graph transformer, right? These are the different answer to one question. How exactly do we aggregate? How do we far we look, like GCN, graph sage, GAT, GIN? These are just extension of this and specifications of this GNN, okay? In the next part, we turn these three-step loop into real mathematics. Okay, we will take our 5% graph, okay, this graph, and compute one full layer of a graph convolutional network by hand. Every number, no skipping, okay? Then we will do the same derivation for graph stage, attention, GIN, and transformers also. So the code afterwards feels obvious for you, okay? All right. Now you understand this update part. You can be like confused about. We will, when we go in detail, like how update things like will work, right? How will it, the weights of Anna goes to activation functions and all, right? So we will get through this also when we update it. So don't worry, you will understand it everything, okay? So this is one part, and now next what we did is, just a minute guys, I need to see something, just a minute. Just a minute guys, I need to see something. There is nothing for your interest, because I had some interest in that, so I had to see this. Okay. Okay. Alright, now let's continue, guys. Alright, so let's start with the classic here. The graph convolutional network, or a GCN. Okay, GCN, graph convolutional network. Okay, KIF, like I will tell you, KIPF and Welling gave us the formula. Okay, here is it, and then dismantle it piece by piece. What is the formula? Okay, formula is H of VL is equal to sigma WL. Okay, U belongs to N of V. Okay, union V, then 1 upon root of degree of V, degree of U, then H of U L minus 1. Let me just write it clearly, because it's just okay, like this, this into H of U to power L minus 1. Okay, it's look very complicated for now, but it's not that complicated, guys. Let me just explain it to you. This was the formula by KIF and Welling. Okay, so this is a graph GCN update rule from the paper by Thomas and KIF and Max Welling. Okay, what is everything? What is this HV in? This is HVL is new embedding, or we can say the feature vector. Okay, feature vector of node V at layer L. Okay, at layer L, you know, I was talking about like layers. It all happens in layers. So what is the feature vector, updated feature vector of node V at layer L? This is like this. Okay, like new feature of node V at layer L. Okay, equal to sigma of W L times the sum over every neighbors of, like every neighbor U of V, right, including the V itself, right, sum of all of this. Okay, into this weight. This is weight. Okay, WL is what? Layer, weight of layer, okay? Layer L into sum of this, of sum of what? Root degree of V times and degree of U. U is the neighbor and degree of V is the V always. Okay, a square root of, and what is H? H is and times the degree of U times the old feature of U. Okay, whatever the U is a neighbor, old feature L minus 1, old feature is what? Feature vector of L minus 1 layer. Okay, so to update Lth layer of V, right, what we did, we multiply the sum, multiply with the weight of layer L with what? Sum of all neighbors and vector itself. What is the sum? 1 upon square root of degree of V and degree of U. U is the neighbor and the feature vector of the neighbor, right? Like this. So this H O L V is like feature vector of node V after layer 1 L. Okay, this is what we are computing. And what is what? Let me give you everything. H of U L minus 1. What is this? This is the feature vector, right, of node V of node U from previous layer, means L minus 1 layer. Okay, these are our inputs here. These are our inputs from neighbor. Okay, inputs. So when we dismantle this formula, this is very simple formula, guys. Okay, that's not very hard. Okay, then we have this part, 1 upon square root of degree of V into degree of U, right? This is term. This is for normalization. Okay, normalization term. You will understand what is normalization, but so popular nodes with many edges would otherwise shout too loudly, right? Like if there is a node which is connected with everyone. Okay, so we have to normalize that. Otherwise they will like, okay, just consider my features only, like this. They will shout loudly means they will influence everyone. So what it will do, this will divide their influence down, so a node with 100 friends doesn't drown out a node with 2. Like, right, influence of a node with 2 connections should be also visible. Like a friend with 100 friends, a node with 100 friends should not like cover up all other influences, right? You can see here, like this is the normalization. Okay, then we have this part, right? WL. What is this? This is the learnable weights matrix. This is the only thing that actually learns when we train our GNN. Okay, these weights will update. Okay, by the training will nudge these numbers. And what is this? This is a like non-linearity some function. It can be ReLU and everything. Okay, so what is ReLU? ReLU of x, like ReLU x is equal to max of 0, x. Without it, stacking layers would collapse into single linear step. So we will understand this also, like a why ReLU, why non-linear. So honest teaching move here, like the square root normalization makes ugly by hand numbers. Okay, so for our worked examples, we will use the simpler cosine mean aggregation only. Okay, because this formula of update, right, of nodes, this is like very we cannot do these by hands, right? When we code, we can use this, but for now it's not feasible. we will use the mean only, right? This we will use the mean, this part only, the mean aggregation. Okay. Just average the neighbors, they capture the same institution with clean arithmetic. Okay. Our when we code this, we will match this exactly. Okay. Then professional library uses the real square root version, and I will show you the small difference. That's the honest way. So let's start with doing something. Okay. All right. We have our node with node 0 with NR, right? Which has feature vector of 1 0. We can write these feature vectors any like horizontally, vertically, that doesn't matter. We have a main with 1, which is 0 1. We have Kera with node 2, which is 1 1. Kera is like studies and play also. So 3 1 0 and LE. 4 is like 0 1, like this. These were the feature vectors. So what I do, I have to like because every node should include itself, right? So we have to, and when we draw the graph, we can add self loop here, like and I sort of studies with Anna also, right? That's not like okay, like this. Anna studies with Anna, Dev studies with Dev, Ben studies with Ben. Okay, this was green. Okay, this was green, right? Let's do this. Anna studies with Anna also. Ben, Dev studies with Dev. Ben studies with Ben. Kera studies with Kera, and like this. Because we are including this all, right? Where we aggregate them, average of all feature vectors we have to take, right? So yeah. For each node, average its own features with its neighbors, right? So let me do Anna node with every by hand here. Okay. So Anna's neighbor set with herself is like this. Like Anna's neighbor is Anna itself and Ben and Kera. Okay, what is the set? Node set 0, 1 and 2. Right? Now average of Anna, Ben and Kera code 1 plus 0 plus 1. Like this. You can say this is this 1 plus 0 plus 1 is 2. Okay. Its second feature in game 0 plus 1 is also 2. So this becomes 2. Right? Now we have to take the average. So how many are there? 3. So 1 by 3 we have to take. So this will become 2 by 3 and 2 by 3. New feature vector for N, which is similar something like 0.66367. 0.667, right? Like this. Then we have to do it for everyone. All right, guys, continuing from here. So we have to do same thing for everyone, right? Like this is for Anna, right? So this is for Anna, right? Now we are going for Ben. Ben is friends with 0, 1, 2. So we have to take the mean of 0. This is a set, right? Mean of 0, 1 and 2 features. This will again go for same because it's same, right? Then we go for Kara. Kara is friends with 3 people. 0 is its 2 and 3. Then mean of this will be 0.75, 0.7, 0.5. Okay. And for then Dave, this is the friend set of Dave is like 2, 3 and 4. And again 0.667, 0.667 is Dave's. This is for layer 1. These are layer 1 calculations, guys. Okay, for every friend. Okay. And Ellie for like this, 4, like 0.5, 0.5. So now the update. So this is aggregation happened, right? Message, then aggregation happened. Now the update part. Okay. Okay. So let's change the color with the white color. With update happened now, right? So multiply by a weight matrix. This is the update, and apply the ReLU for on it. Okay. So for the demo, just let's take the weight matrix W as this. W is this. 1 minus 1, 1, 1. This is the weight matrix. Okay. So for any row A comma B, multiplying by W gives us like any, there is a vector, right? A, B, any vector. What it will do? A plus B, then minus A plus B, right? So it is not like that. Okay. Okay, so it's like this. Let me draw something for you. 1 minus 1. Okay, it was right. Earlier it was right, like this. So this will give us A plus B, and this will give us B minus A. Okay, if we multiply something like this with this. So first output A plus B, and second output is B minus A. So this is the weight matrix for us. If we multiply anions aggregated, you know what happened now? According to the formula here, we have our weight matrix, right? And we have our mean, this. Now we are multiplying this. After multiplying this, we will apply this function, which is ReLU. Then we will have this updated weights for N. and every friend, okay, for layer 1, right? That's what I am doing right now. So you can see what is n vector. This is w is like 1 1 minus 1 1, n is like 0.667 and 0.667. So it will give us a plus b is what, 1.334, and a minus b is equal to same, then b minus a, this will become 0, right? So now we have to push through this ReLU. What is ReLU? ReLU on x is equal to max of 0 comma x, right? Now what is this? If we are ReLU on this 1.334 and ReLU on 0, so what it will give? It will remain same, because 334 is this, 0 will remain same, okay, like this. This is for like ANA, right? This is for ANA. This is updated ANA. So h of ANA, which was 0 node or at layer 1, is equal to this, okay. Now we will do this thing for everyone, and we will get like this. Ben will get this 1.33 because it was same, right? And then Kaira will get this 1.25 comma 0, and they will get 1.3330, and then Ellie will get 1.0 comma 0. Now look at what happened here. Anna and Ben ended up identical. Anna and Ben, they are identical because they share the same neighborhood, okay. Ellie of the edge of the graph with only Dave, okay, ended up different, right? Very different, 1 and 0, right? So the structure changes the feature. That's the GNN doing in one job, okay. So in next part we will run code of this, and that will print the exactly these numbers, okay. Like other 4 architectures are like like graph sage, concat, like that, and graph attention networks, everything, and graph isomorphic networks, okay, GIN, and graph transformers. They are like very similar, okay, just skeleton is same but different muscles. Let me explain it to you also what I mean, okay. So we already found the GCN, graph convolutional network update equation, right? Now we will understand Alright guys, so this was GCN, graphical convolutional network. Okay, graphical convolutional network. This was the update rule for it. Now we understand the graph sage. Okay, graph sage. What is this? So unlike a GCN, which mixes neighbor features using normalized sum, and in graph sage, it first aggregates the neighbors, then concatenates the nodes on features with the aggregated neighbor feature, and finally applies a learnable transformation. Like I can this is like h of VL is equal to this WL, we can say dot concat. Okay, and h of V of L minus 1 comma aggregated h of U L minus 1 where U is neighbors of V, like this. Okay, first aggregate all the neighbors, then concatenate with the node V and multiply with weight and apply the non-linear ReLU on it, right? So this was our so new feature of V equals to sigma of W times concatenation of V's own old features with aggregated feature of its neighbors, right? That's the core idea. So here the new idea is the concate, right? What is the new idea? Is concate, right? Now, instead of blending yourself into average, okay, you keep your own vector and your neighbor summary side by side. Okay. Now let W mix them, and it samples a fixed number of neighbors rather than using all of them. Okay. So which is what lets it scale to graph with millions of nodes on screen. Okay, that's what graph says for us, guys. And now we understand what is graph. This is variation graph attention network. Okay, whatever it is. GAT. So what is his specific let me show you. So update formula for this is this: h of V of L player, okay, is equal to rho sigma U is the neighbor of V, okay, and alpha VU. You will understand this, and W of HU L minus 1. So the core part of this is not every neighbor, okay, is equally important. Okay. So instead of giving every neighbor the same weight, okay, or a weighted or a weight based on all node degree, GAT will learn an attention score for each neighbor. So what is this? V is the node, U is the neighbor. For each neighbor, VU, right? GAT, graph attention network, will learn this alpha value, which is called attention score. Okay. All right. So it's, if we say like a new feature of V equals to sigma of sum over neighbors, right, of V, okay, of alpha vu times w times u's old, u is the neighbor, right, old weight feature. Okay, the star of this equation is this alpha, which is called the attention coefficient. Okay, how much node v should listen to node u, this will decide. Okay, and how we calculate this? Alpha vu is equal to softmax u, then we use leaky ReLU on a transformation w into hv or w hu, like this. So these alphas are learned, right? We can learn them. Okay, they are all positive and they are all learned and they are all positive and across a node neighbors. So these alphas are learned and they are all positive also, and across a node's neighbors they sum to 1. Okay, like alpha vu1 plus alpha vu2 dot 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 alpha vun, this all sum to 1. Okay, like this. And a proper weighting training adjusts them by back propagation, so the model will discover which connection are important. Okay, notation is like this. So just this is the all, but we have to understand this equation in little more detail, right? So what is this? Alpha vu is equal to softmax on u, then leaky ReLU. Okay, A transpose, okay, WHV or WHU, like this. So this equation is the heart of the attention graph attention of GAT. Okay, this is the heart of GAT. It tells us how the attention coefficient is computed. Okay, so that is how much importance node V should give its neighbors U. Okay, so what is HV here? What is HV? Right, this is the feature vector of the target node. Okay, this is, and what is HU? This is the feature vector of the neighbor. Alright, and we compute this WHV and WHU also. So before comparing nodes, GAT first transform them using a shared learnable matrix. Okay, this is shared learnable matrix W. Okay, learnable matrix, and these are feature vector of V, and this is feature vector of U, which is the neighbor, right? We transform them and then we concatenate it. Okay, concatenate. Okay, concatenate this whatever vector we find after it. Then AT is the learnable attention vector. Okay, AT is the learnable attention vector. Alright, so we can learn this also. Then we multiply this with and go through the leaky ReLU after this. Leaky ReLU is like, let me tell you what is leaky ReLU definition. This is leaky ReLU, guys. Leaky ReLU of x is equal to x if x is greater than 0, else 0.2x, like some value here, okay, if x is less than 0. Alright. So like output remains there. So say unlike ReLU, leaky ReLU keeps a small negative slope, like it does not exactly make it directly 0, right? It keeps a negative slope which helps the gradient continue to flow during the training. Okay. Then after that we apply softmax. Okay. When we apply everything with its neighbors, when the softmax is alpha of I is equal to E of EI upon J E of EJ. Okay. So whatever value we get, right, from this part, leaky ReLU, right, this we call the EI, and we make this EI to like this. Softmax is like this. J is the neighbors, okay, and EI is the target node. Okay. This is what values means, and yeah, that's what. So take the target node and one neighbor and transform their features, place them side by side, concatenate them, and score their relationship with learnable vector, and apply leaky ReLU after that. Then normalize the score across all neighbors using softmax. The resulting value is the attention coefficient that determines how much the neighbor should influence the target node. That was our GAT, graph attention network, right? Then we have graph isomorphism network. What is this? We have a GIN, graph isomorphism network. We have this. Okay. What is GIN? This is the most expressive of the classic GNN. Okay, like you can see like this. What is the formula for this? I am writing that formula. Formula for this is like this: H of VL, okay, is equal to MLP of 1 plus epsilon H of V L minus 1. Okay, so these V and V are same, right? Plus sigma U is from the neighbors of V, H of U L minus 1. So GIN was designed with one main goal of what? We have to make the graph neural network as the powerful as a so there is a thing called Weisfiller layman, okay, WL we can say, okay, graph isomorphism test for distinguishing graph structure. So this GIN was introduced by K.U. Luke Zhu and collaborators of his. Okay, KULUG. It was introduced by KULUG. Okay. So so what is this term? This term, right? This is one of the most important ideas here, because instead of giving a node a fixed weight of 1, what we do? We give GIL learns how much importance to give the node itself also. This is the aggregation, just normal aggregation. But how much weight one should give itself, right? So we can learn that also. Okay. If we make it 0, then it will become 1. Then it is like normal aggregation. Okay. We can reduce, we can give it negative value, we can give positive value. If we are giving 0.5, it minus 0.5, so weight of the node V itself will reduce. Okay, how much weight we are giving like this, right? What is MLP? MLP stands for multi-layer perceptron. Okay, it's like multi-layer perceptron. Okay. Unlike GCN, which applies just one linear transformation followed by activation, GNN uses a small neural network for this. Okay, like for example, input, then linear, then ReLU, then again linear, then output. Like this, a small neural network, like multi-layer perceptron is called neural network. This makes GNN more expressive also. Okay. And why GIN using this plain sum here? So this is the main idea behind GIN. Compare 3 aggregation methods for neighbors values like this. Wait a minute. So how we read this? New feature of V equals to MLP of what? 1 plus epsilon times HV times V's own feature, right? Plus plain sum of neighbors features. Okay. So 2 new pieces are there. Epsilon is here, is a small number weighting how much, okay. No, the secret is here is the sum is injective. Means what? This plain sum is injective here. Sum is injective. So by which what we are doing? Different neighbor multiset give different totals. Like whereas mean and max can blur 2 different neighborhoods into same value. Okay, but different neighbor multiset give different totals. Alright, so why some beat the mean? The isomorphism trap. So here why that matters. So 2 small graphs, both with every node of degree 2. Okay, for example, so let's say there are 2 graphs, 1, 2, 3, 4, 5, 6. So this is one graph and one is this graph. Okay, now 1 is 6 cycles and 2 is triangles. Both graphs have same number of nodes. Okay, and same number of edges also. But every node has exactly neighbors, two neighbors. Okay, each node has exactly two neighbors also. So a GCN leaning on mean or max pooling smooths away the difference and hence both graphs in the same embedding, right? So it literally cannot tell them apart because averaging isn't injective, right? So two different structures collapse into one representation. So this is the problem with classical problem. The classic Wheeler-Lehman test was built to detect. So a simple surprising powerful procedure for checking whether two graphs are structurally identical. GIN was deliberately designed to match the WL test power, and which is why it can separate structure that GCN maps to the same point. Okay. So we can do this like GIN is similar to WL test expression. This is the similarity expression. Okay. Now we come for like guys graph transformers, right? So transformers is for global attention. Okay, like global attention means every node can, okay, in principle attend to every other node, okay, not just its neighbors. So it's great for long range dependencies and messy graphs. Okay. Okay, guys. So let's say we have a node embedding matrix H. Okay, and first three line projections Q is equal to H times W. Okay, WQ, and K is equal to H times WK, and V is equal to H times WV. What is this? Like queries are what a node is looking for. Q is query. Okay, so query, this is query matrix. What node H is looking for. Okay, K is the key. Okay, it's like key is what it offers, and V is value, which means what actually gets passed along. Then the attention itself. So attention is what? So attention of q comma k is equal to softmax of q k transpose, okay, upon square root of d plus b, okay, into v. So softmax of q times k transpose over the square root of d plus b all times v, okay. So compares every node's query, okay, to every node's key. So v divided by d square root of d to root the key dimension, okay, root of the key dimension, dk we can say, right, to keep the numbers stable. And here is the graph specific twist, like bias term b, like so this is the bias term, this is graph specific only, okay. Standard transform use only embedding similarity. So graph transformation add b to inject the structure, whether two nodes are connected, how far apart they are, what edge type joins them, right. Softmax turns scores into weights that sum to 1, and we take the weighted blend of value vector. So we don't do this once, okay. So in multi-head attention, what we do, okay, in multi-head is equal to, we have to concatenate of head 1 to head h, okay, times WO. We run several attention heads in parallel and each with its own QKV, then concatenate their outputs and pass them through a projection matrix WO to merge them. After that, a small feed forward network FFN will two linear layers with a ReLU between, okay, like linear, ReLU, then linear, okay, defines each node's vector, and through residual connection plus residual connection add the input back to the output, plus layer normalization plus normalization. Keep training stable, we can keep track many layers. So edge cases, okay. So before code, the trap expert watch for like over smoothing, stack too many layers and every node's feature coverage to the same blur, right. So more layers is not always better, okay. 2 to 4 is often a sweet spot. So over squashing information from faraway nodes get crammed through narrow bottleneck edges and it's lost. So part of why a global attention transformer exists, okay. The expressivity ceiling, plain message passing GNN cannot exceed the WL test, okay. So some structures are probably indistinguishable no matter how you train, okay. So the cost is dense graph make urgency metric huge, and graph size sampling and sparse operations are how you survive millions of nodes. So keep these in your head, and they explain nearly every design choice in the code we are about to write. So we are going to code now. So thank you guys for watching. We will meet you in next video where we code this, okay. This was the only